Let us talk about wavelet. We'll give a brief introduction of wavelet. So when we talk about wavelet, we need to talk about Fourier transform also, because in DSP and image processing we use Fourier transform, and because wavelet is an aspect of or going increasingly being used in this field, so the Fourier transform, we represent a signal in terms of sinusoid. So Fourier transform provides a signal which is localized only in the frequency domain. This is very important. Fourier transform is localized to Fourier domain. We don't have a time domain aspect. It does not give any information of the signal in the time domain. But basis function of the wavelet transform, which are small waves, are located in different times. So time aspect is also coming. So they are obtained using scaling and translation of scaling function and wavelet function, which is the important aspect of wavelet transform. So the WT is localized in both time and frequency. So we have time as well as frequency, whereas in Fourier transform we had only this frequency domain. So in addition, the WT provides a multi-resolution system. This is also important, and multi-resolution is useful in several applications. For instance, image communications and image database. So if a signal has discontinuity, Fourier transform produces many coefficients with large magnitudes. We have large magnitudes, significant number of coefficients. But WT, that is wavelet, generates few significant coefficients around the discontinuity. So nonlinear approximation is a method to benchmark the approximation power of a transform. In nonlinear approximation, we keep only a few significant coefficients of a signal and set the rest to 0, since we reconstruct the image using the significant coefficient. This is very important. Fourier transform has a large number of coefficients. Wavelet produces less number of coefficients. WT produces a few significant coefficient for the signals with discontinuity. Thus we obtain better results of WT nonlinear approximation as compared to our FT. Most natural signals are smooth with a few discontinuities. For example, speech and natural images are such signals. Hence, WT have better capability for representing these signals as compared to FT. So good nonlinear approximation results in efficiency in several applications like compression and denoising. So what is a wavelet? Wavelets are actually essentially mathematical functions. What it do? Cut up data into different frequency components and then study each component with resolution matched to its scale. And why it is required? Analyzing discontinuities. Again, discontinuities we have just talked about, and sharp spikes of the signal. The applications which we talked about are image compression, human vision, radar, earthquake predictions, and these are the numbers to name a few. There are a wide variety of applications in which wavelet are being used. So what existed before this technique? Approximation using superposition of functions since early 1800s, and Fourier discovered that he could superpose sines and cos to represent another function to approximate these choppy signals. So these functions are non-local and stretch out to infinity. So these do a very poor job in approximating sharp spikes as well. So when we talk about wavelength, we have mother wavelet. This is analyzing wavelet prototype function. Then I have temporal analysis performed with a contracted high frequency version of the prototype wavelet, and frequency analysis performed with the dilated low frequency version of the same wavelet. High frequency, low frequency. Then basis functions, basis vectors which are perpendicular or orthogonal to each other. The sines and cosines are the basis functions and the elements of the Fourier synthesis. So scale varying basis functions are also there. The basic functions varies in scale by chopping up the same function or data space using different scale sizes. If we consider a signal or the domain from 0 to 1, dividing the signal with two-step function that range from 0 to half and half to 1, and 4-step 0 to 1 by 4, 1 by 4 to half, half to 3 by 4, and 3 by 4 to 1. So each set of representation code the original signal with a particular resolution or scale, and Fourier transforms translating a function into time domain into a function in the frequency domain. So these are the fields where we are using wavelets. Fourier transforms have single set of basis functions like cosine and cosine, as we see. Time frequency tiles we have, Coverage of the time frequency plane is also there. But wavelet transform have infinite set of basis functions. Debauche's wavelet basis functions, we have Haar, to name a few. Time frequency tiles are there. This is very important, and coverage of the time frequency plane is also there. So how do wavelets look like? If we see Haar, we have Debauche's, we have Couplets, we have Simlet. So trade-off between how compactly the basis functions are localized in the space and how smooth they are. They are classified by the number of vanishing moments. So filters and coefficients, we have smoothing filter like a moving average. Data detail information is also there. These are certain applications like artificial vision of robots. We have compression, we have denoising of data, and musical toning. So sound synthesis can also be done. So thank you so much. Take care of yourself.